Is the expansion of the universe a falsehood? Turning to this question a new way, some open-minded scientists are now answering this question. Perhaps we are living in a boundless vault that could resolve the mystery of the so-called expansion of the universe forever. Even this void can give us information about blueprint as well as reasons why there is an entire universe. So, what exactly is this void, and how did scientists think of the idea that the universe is expanding? One of the biggest questions of cosmology is the rate at which the universe is expanding. The Hubble constant, h0, is an expansion rate among experts as a result of which. Edwin Hubble is famous to many for the well-known space telescope, but few people know that Edwin Hubble, the man behind the name for the space telescope, was one of the astronomers who worked out the idea of the expansion of the universe with certain observations. Hubble observed the movement of the galaxies in 1929. Today, that Hubble constant is the rate for how fast the universe is expanding in kilometers per second per megaparsec, kT-s and MPC. About 3.26 million light-years is 1 megaparsec date 0 seen. From Hubble was a few hundred kilometers per megaparsec, which is up from today's estimates. Within the range of modern estimates, around 67 to 74 kilometers per megaparsec. The new estimates are from Type 1a supernovae observations, Cepheid variables, and the cosmic microwave background. In fact, determining the Hubble constant primarily depends on the microwave background. It seems to be the faint glow that's left from the Big Bang. A Hubble constant of about 67.4 kilometers per megaparsec can in fact be read from a very accurate map of the cosmic microwave background, thanks to the European Space Agency's Planck satellite. On top of that, the radiation also shows very clear evidence of the universe drifting apart. One of the big pillars of the theory of an expanding universe is the cosmic microwave background. Type 1a supernovae have been observed with increasing frequency by Hubble Space Telescope, and even higher estimates of 74 kilometers MPC have been derived. These supernovae, also called standard candles by scientists, have known absolute brightnesses allowing for what science calls distance measurements, which provides us with a way to determine the expansion rate of the universe. The first significant difference between these two measurements is that one is struck by a source much older than the other. The cosmic background radiation is from the early universe, and supernovae are recent. It's the Hubble tension, what astronomers and astrophysicists call a discrepancy, and it ponders legitimate questions about how we understand cosmic history and basic physical theory. But some scientists are claiming that to resolve this tension, we may need to change the entire physics. These theories are more than standard model of particle physics theories about exotic forms of dark energy or modifications of gravity. Is it going wrong to assume expansion? Would it surprise you if I told you that, yes, the whole Hubble constant could be wrong? There are observations without which the standard assumptions cannot be upheld. For instance, El Gordo, the massive galaxy cluster just discovered, is so early in the cosmic timetable and so massive that it doesn't fit at all with the standard model of cosmology. Such observations lead us to believe that some traits of the universe could be somewhat other than what we had thought. But further dimensions of the problem are given by observations of the large-scale structure of the universe. The cosmos looks to have clusters of galaxies and superclusters distributed in a way not well described by what we know now about the expansion. It is an urgent need for clarification, and we really need to figure out how to understand the presence of mysterious dark matter and dark energy. Normally, galaxy separation expands with the expansion of the universe. Hubble's law tells us that if they moved away from us, we'd see them move faster, because the faster you go, the farther you go since the distance is linear. Because the universe expands equally in all directions, the further away that a galaxy may be from us, the faster it goes away from us and is proportional to its distance from us. However, it could not be proven and observed all over the universe in an uniform expansion. Perhaps the expansion region is simply accelerated or slowed locally by other structures in the cosmos. Aside from that in the above, finding anomalies in the motions of galaxies that can't be explained by gravitational effects of known matter brings us another interesting point. To give one example, the outer parts of a spiral galaxy rotate at faster speeds than the mass of visible stars and gas clouds, assuming standard physical parameters would have us expect. One other thing this gave rise to was the assumption of the presence of dark matter. Mysterious force behind the accelerated expansion of the universe is said to be dark energy. But as it stands, we do not know very much about dark energy and dark matter. In fact, they have not been proven to exist. Does Euclid have the answer? If all goes as planned, the European Space Agency, ESA, Euclid mission, which is ambitious, to say the least, will finally shed some light onto the universe. Since fall 2023, the brand new space telescope has begun surveying the universe again. Euclid will scan out to what we can see as far in the universe to build a giant sky map. And this map should help us understand how galaxies move, help us understand the expansion of the universe and solve the mystery of dark matter. This telescope was named after the ancient Greek mathematician Euclid, who was specially designed to display many stars in a clearly arranged space and to understand the movements and dynamics of invisible space. The motions of galaxies are a fascinating field of research that will not only have us better understand the expansion of the universe, but also help us better understand nature of matter, energy, and fundamental laws of physics. Are we living in a huge void? And you have the perfect right to wonder, what's this all got to do with whether or not there could be a giant void that is so vast that it contains us all? But this intriguing idea could help to crack some of cosmology's biggest mysteries. Suppose our piece of the universe is a cosmic void, or relatively underdense, a circumstance that impedes an accurate measurement of the rate of expansion of the universe. It could also be that other parts of the universe are more dense, and that galaxies don't move quite the same way over there. If this hypothesis is correct, it should help explain some of the discrepancies other people have had in getting the Hubble constant and in tracking how the galaxies move. It is possible that the theory we are in a vast void is the explanation for this tension between them. If such a void existed, measurements of the expansion rate would thus naturally be influenced by the local matter density here, due to the fact that the gravitational effect of such voids would differ in more dense regions of the universe. They add that there could be outflow of matter from the void into other areas due to gravitational pull from surrounding denser regions, perhaps speeding up what is known as the local expansion rate. What's interesting is that data on direct counting of galaxies in different regions show that maybe, in fact, we are really living in such a local void. It wasn't going to be a completely empty void, but it would have a density of about 20% lower than the mean of the universe, and it would stretch out to some 1 billion light-years. To examine that hypothesis, one of the methods employed was modified Newtonian dynamics, MOND for short. MOND was originally proposed as a way of explaining anomalies in rotational velocities of galaxies, a problem which is solved by dark matter in conventional theories. A MOND universe is one where structures, such as galaxy clusters, grow faster, and the local expansion rate also varies. What are new observations of galaxy motions, in particular of the so-called bulk flow? The average speed of matter in a given sphere? These observations indicate that, on a scale of 1 billion light-years, the bulk flow is 4 times the standard model value and gets larger with increasing region scale. Contrary to the standard model's predictions, this further supports the local void in which our Milky Way must also be. What's the effect of emptiness on life on Earth? So, are you wondering if this makes any difference to our galaxy and our life within? More importantly, the existence of such a void around us could actually help explain how our galaxy and its neighbors actually work. Any such voids would pervade a universe and create gravitational forces and dynamics of galaxy motions that would differ from those scientists currently understand. Basically, this hypothesis would imply that all our galaxy and all orbital galaxies are suspended in a kind of astronomical balloon that is different from the denser areas of space. Then this void can influence how our galaxy developed and eventually fell. The long-term development of the Milky Way is dependent on the collisions and interactions that a galaxy experiences in its region of a lower density. The resulting correlations could affect star formation, gas and dark matter distribution, and structures within the Milky Way. Right now, we are beyond the influence of this void. The discovery of this possibility has a big deal for our scientists. Maybe textbooks will even be changed. None of this you and I does not notice in day-to-day life. In an interesting way, however, the assumption of life in a void is intriguing. This could mean that if our galaxy lives in this less dense part of the universe, our life conditions may be very different from the rest of the universe. Yet the reason we haven't found other types of life is that we think we're living in a very sparsely populated piece of the universe, and that's why we haven't been able to. That's what scientists are saying. Maybe the conditions in other regions are different, and there are many planets in a solar system that have some life, or even entire star systems that are hugely populated. Exciting ideas like that could have consequences for how we search for life. But the hypothesis of a local void will certainly also change the way we think about the future of the universe. If such a void affected the expansion rate of the universe locally, that could signify that the future of the universe will be much more complicated than we thought. Scientists believe that the expansion must inevitably end at some point in one of three scenarios. Either the universe starts to freeze again, or the universe freezes since it can't expand any further, or it suddenly contracts like a rubber band. These scenarios no longer work if we have regions of various expansion rates, and sometimes these regions may even balance each other out in ways we don't currently understand. However, last but not least, we must consider the possibility that there was actually no single starting point where the universe began to expand. Serious theories exist that would say the universe's starting point is not just one, maybe several, or that the universe hitches a ride on itself, feeds itself like an eternal whirlpool, but become a subscriber now to never miss an incredible video.